Hello and welcome back to Math 220A, Mathematical Logic. Lecture 6, Gödel's Completeness theorem. We begin the discussion today by establishing some further auxiliary properties about formal proofs, and then we will arrive at the formulation of Gödel's completeness theorem, and we will begin considering some of the rephrasement and reductions that will be actually used in the proof of Gödel's completeness theorem. But let us begin with a useful lemma about formal proofs, the so-called simulation of constants by variables let psi be an L formula, as usual in some fixed language L, T an L theory, and let C be a set of constant symbols such that C has no intersection with the language L. So all of the constant symbols in C are mu and are not already appearing in L. Then we have the following two claims. A, let x be a variable, and C an element of the set capital C, the set of constant symbols C. Then the following are equivalent. 1, T proves the formula psi. 2, T proves the formula psi with C substituted in the place of x. But of course now we have to talk about probability in the language in which the formula psi makes sense. Since it's using a new element not appearing in the language L, we have to work in the extended language L union C. And 3, T proves, again working in the language L union C, the formula psi. So all of these three claims are equivalent. And part B, we have that T proves the formula psi in the sense of the language L if and only if T proves the formula psi, but now in the sense of the language L expanded by all these new constant symbols from the language C. So at the very least it tells us that when considering formal proofs, when we add a bunch of new constant symbols, so in principle the language becomes bigger and the set of all formal proofs in this language also becomes bigger. But what this lemma is telling us is that it doesn't change probability if we add some more constants to the language. Proof. To simplify the notation, we will assume without loss of generality that T is empty. So this will allow us not to write T every time, but the general proof, in the case for general theory, T is identical. So the case of general T is the same verbatim. So let's begin by proving part A. First we show that 1 implies 3. This implication is clear simply because any L proof is also, in particular, an L union C proof. So hence, if we can prove it in a smaller language, then of course we can also prove it in the bigger language by reusing the same formal proof. Next, let's consider the implication 3 implies 2. If psi is provable in the sense of the language L union C, then applying the generalization rule, we get that also for all x psi is provable in the same language L union C. We also know, by an example considered in the previous lecture, that the formula for all x phi implies phi with t replacing x is provable in an arbitrary language for phi, an arbitrary formula. This holds for any formula phi and term t. In particular, we can apply it to our situation by taking phi to be psi and the term t to be the constant symbol c. So we have that for all x psi implies psi with c substituted in the place of x is provable in the sense of the language L union C. Hence, by modus ponens, we get that the formula psi with c substituted in the place of x is provable in the sense of the language L union C. Next, we consider the hardest implication, 2 implies 1. So we need to show that if psi with c substituted in the place of x is provable in the sense of the language L union C, then this implies that psi itself is already provable in the sense of the language L. We set up some notation. Assume that phi tilde is an L union C formula. So a formula in the language L together with a constant symbol for C. And assume that y is a variable not occurring in phi tilde. Then we will denote by phi and also by phi tilde with y substituting c the word obtained by substituting every occurrence of c in the formula phi tilde, which remember is a formula in the language L together with the constant symbol, by the variable y. Now let phi tilde, psi tilde, and chi tilde be the formulas in the language L together with the constant symbol C formulas with no occurrence of the variable y. Then we have the following claims. First, we have that phi is an L formula. So again, note that we denote by phi the result of substituting the constant symbol c by the variable y. Second, phi with c substituting y is equal to the original formula phi tilde that we started with in order to obtain phi. And so now if we substitute the constant symbol c back instead of the variable y, we get the formula phi tilde. 3. If phi tilde is an equality axiom, respectively a tautology, or a quantifier axiom, then the formula phi is also an equality axiom, respectively also a tautology or a quantifier axiom. And 4, if phi tilde is obtained using the modus ponens rule from two formulas in the language L together with the constant symbol c, the formulas psi tilde and chi tilde, then the formula phi associated to phi tilde is obtained using the modus ponens rule from the formulas psi and chi associated to the formulas psi tilde and chi tilde by substituting the constant by c by the variable y. And finally we have 5. If the formula phi tilde is obtained using the generalization rule from the formulas psi tilde, then the formula phi associated to it is obtained using the generalization rule from the formula psi associated to the formula psi tilde. Let us provide proofs for some of these claims. Claim 1 follows by a straightforward induction on the height of the formula phi. The second claim follows from our early discussion of the rules for simultaneous substitution. Recall that if we have a formula theta and we have a variable x and assume that S is a term not containing any variable with an occurrence in theta then the result of substituting x by s in the formula theta is what we defined as the naive substitution back then. So this is just the word obtained by replacing every occurrence of x by s in the formula theta. Hence, in claim 2, our term is the constant symbol c, and our variable is y, and we substitute in c instead of y in phi. And applying this remark, we obtain the word in which every occurrence of y is replaced by the constant symbol c, which is exactly the original formula phi tilde. 4 and 5 are immediate. Because in each of the formulas we perform the analogous substitution, replacing the constant symbol by the variable. Hence, if the modus ponens rule applied to obtain phi tilde from psi tilde and chi tilde, after this substitution, we see in the same way that phi is obtained from psi and chi, and similarly for the generalization rule in 5. Similarly, by inspection, we immediately get the claim 3 for the cases when we have an equality axiom a tautology or an instance of the quantifier axioms corresponding to Q1 or Q3. So the only non-trivial case corresponds to Q2. Towards this purpose, assume that phi tilde is of the form as in the axiom Q2, so it is of the form delta tilde with some term t substituting x implies exists x delta tilde, where delta tilde is an L union C formula and t is an L union C term, then we have to prove that the formula phi obtained from phi tilde, which is given by substituting the variable y in place of the constant symbol c. So it is the formula delta tilde, t substituting x, now y substituting c, implies exists x delta tilde, y substituting c, and we have to show that this formula phi is itself an instance of the quantifier axiom Q2. This claim follows from the fact that the formulas delta tilde with t substituting x and with y substituting c, and the formula delta tilde with y substituting c first, and then the term t with y substituted in the place of c, substituted in the place of x, are equal, and this can be checked by induction on height. Now, having established these claims 1 through 5, assume that we are given a sequence of formulas phi tilde 0 through phi tilde m, which provide a formal proof of the formula psi with c substituting x in the language L union the constant symbol c. So all of these formulas phi tilde I are allowed to involve the constant symbol c. Then we choose a variable y not occurring in any of these formulas, so in any of phi tilde 0 through phi tilde m, and also such that y is not equal to x. Then the claims 1 through 5 show that the sequence of formulas phi 0 through phi m, where phi I is obtained from phi tilde I as defined before, so by substituting the variable y in place of the constant symbol c, is a formal proof in the language L of the formula psi with c substituting x and y substituting c. As in these claims, we have verified that substituting the constant c by a variable preserves the deduction rules and the logical axioms. And now this formula is, of course, equal to the formula psi with y substituting x, and this holds by our earlier discussion of the simultaneous substitution behaving like naive substitution in the situation when when there's no conflict of variables, when the variable doesn't occur in the term. So this gives us the formula psi with y substituting x being provable in the language L, but then by the generalization rule we get that the formula for all y psi with y substituting x is provable in the language L. We have seen earlier the following examples of provable formulas. This is an example from the previous lecture. If the variable z does not occur in the formula theta, then we have that the formula for all z theta with z substituting x implies for all z theta is provable for as long as theta is an L formula and x is some variable. And we also saw that the formula for all x theta implies theta is provable. Hence, combining probability of the formula for all y psi with y substituting x and the probability of this formula with theta taking theta to be psi, we conclude by modus ponens that the formula for all y psi is provable, and then using the second formula with theta equal to psi and modus ponens again, we conclude that psi is provable in the language L, which completes the proof of item A in the simulation of constants by variables lemma. Now we'll see that item B of the lemma is a direct consequence of item A. B says that T proves psi in the language L if and only if T proves psi in the language L union C, where C is an arbitrary set of constant symbols not contained in the language L already. So the intersection of L with C is empty set, and T is an L theory, and psi is an L formula. To see that this holds, note that any L union C proof involves only a finite number of elements of C, the set of constant symbols. So we may assume that the set C is finite. Then we can conclude by induction on the cardinality of this finite set C using the equivalence. 1 is equivalent to 3 in item A. So we are adding one new constant symbol at a time, and we know that the equivalence of 1 and 3 in A tells us that this equivalence of probabilities holds when just a single new constant symbol is added. And so we apply this inductively, first to the language L. So for example, if C consists of C1 through Cn, finitely many new constant symbols, first we apply it to the language L and a new constant symbol C1. Then we take this to be the language L1, and we apply now the same equivalence 1 to 3 to the language L1 together with the new constant symbol C2, etc. So inductively in finitely many steps, we still obtain an equivalence, which finishes the proof of the simulation of constants by variables lemma. We will also need one more auxiliary lemma. Let T be an L theory, phi of x an L formula, with the single free variable x, and C a constant symbol, not occurring in the theory T union the formula phi of x. And assume also that the theory T is consistent, so it doesn't prove phi and not phi for any formula phi. Then we have that T union the formula exists x phi implies phi with C substituting x is a consistent L theory. Proof. Recall that by a corollary to the deduction lemma, we know that if T is an L theory and phi is an L sentence, then T proves phi if and only if T union the negation of phi is inconsistent. Applying it to the formula that we are given, if the conclusion of the lemma doesn't hold, we have that T proves the negation of this sentence and note that it is a sentence because the only free variable of phi is x and it is quantified or substituted by the constant here. So we have the negation which can be rewritten by remembering that implication is an abbreviation. So if we spell it out, we get that T proofs exists x phi and not phi with C substituting x. So in particular, T proves the first conjunct of this conjunction. So T proves exists x phi. Also T proves the second conjunct. So T proves the negation phi C substituting x, which by the simulation of constants by variables lemma, part A is equivalent to T proves the negation of phi. By the generalization rule, this tells us that T proves for all x not phi. We also have an instance of the quantifier axiom Q3, which tells us that exists x phi if and only if not for all x not phi is a logical axiom. Hence, in particular, we can apply the modus ponens rule, since T proves exists x phi, and here we have in particular that exists x phi implies the right part. So by modus ponens, we conclude that T proves not for all x not phi, but then we obtain that T proves the formula for all x not phi and its negation, which implies that T is inconsistent, contradicting the assumption, and so proves the lemma. Finally, we are ready to state the first main theorem of the course, Gödel's completeness theorem. Let T be an L theory and phi an L sentence. Then we have that phi is a logical consequence of T, a purely semantic notion defined in terms of satisfaction in structures, if and only if T proves phi, a purely syntactic notion defined in terms of syntactic objects, formulas, and formal proofs. First of all, we make the following remark. Since we know that the notion of logical consequence does not depend on the language L, in the sense that as long as both T and phi are L formulas, the implication holds in the sense that any L structure realizing T also has to satisfy phi, and since by Gödel's theorem the two notions are equivalent, it follows that a posteriori the notion of provability in the sense of the language L does not depend on L either. So once the proof of Gödel's completeness theorem will be completed, we will write simply provable without specifying the language instead of provable in L. But of course, in the course of the proof of Gödel's completeness theorem, we still have to stick to with the notation from the original definition of formal probability, which relies on the language in which we are considering our proofs. First, we can consider the easy direction, namely, if T proves phi, then T also has phi as a logical consequence. So this is the easy direction of Gödel's completeness theorem. We already know that it holds by soundness of our notion of formal proof. Hence, the difficult direction is to show that if phi is a logical consequence of t, then it is also provable from t. So this requires to exhibiting a formal proof in the situation when phi holds in all of the structures that satisfy t. We have the following two observations. Assume that phi is not a logical consequence of t. This holds if and only if t union the sentence not phi has a model. So this is just by definition of logical consequence. And we also have that if t does not prove phi, then and only then t union the negation of phi is consistent by corollary to the deduction lemma. In view of these two observations, we see that the Gödel's completeness theorem is equivalent to the following theorem. A theory T has a model if and only if it is consistent. Again, the first part of the equivalence is a syntactic notion, admitting a model, so being satisfiable, all of the sentences in T being satisfiable in some structure. And the second part is syntactic. It talks about T being able, not being able to prove any sentence phi simultaneously with its negation. We will begin the proof of this theorem in the next lecture.